All right, let's begin. I've been getting a lot of emails from the Writing Center, and some of them are for appointments that were in the middle of last week. So I don't think they send me a message as soon as you walk out of the door. So if you've noticed online that you did the appointment but you don't yet have the points for it, don't panic, because I think they're sort of trying to catch up on a little bit of a backlog. All right. Today's the last day to actually have the appointment. It's not the last day to make the appointment. So I hope that everybody's done that. Our next homework assignment is due on Tuesday, and the majority of the problems in that assignment are related to the stuff we did last Thursday in class, and then the last question is related to the landfilling in-class exercise we're going to do today. Also, at the end of this week, on Thursday, before you go for the long vacation, we'll have our final quiz of the semester. So you got that to look forward to. And we're continuing our discussion of solid waste management. And before we get into the new material, any questions on these announcements? Well, let me give you just one more point of information on the project. Now, it says this in the assignment description, and I'd really encourage everyone to take one last look at that as you're putting together your final draft. But the whole idea is of these draft submissions is that it gives you a chance to break the assignment into pieces. So part 1 and part 2 should be edited again after the draft submission and combined. So the final thing that you submit is the combination of part 1 and part 2, and it's been perfected over time because you improved it based on my comments, you improved it based on what the Writing Center told you, and also you've probably been learning more about the topic along the way. So that final polished version, you'll give me a paper copy during our last class, and you'll also upload a digital copy to iLearn so that I can do the plagiarism detection. And also, I just like to have a copy of student papers for assessment reasons. Any questions about the project? All right. Let me give you one piece of information that you'll need for the last problem on the assignment. The last problem on the assignment, I ask you to do a book problem. And it's one of those where they tell you to refer to the data from an earlier problem earlier on. Since you didn't do problem 11.7 on this assignment, let me just give you some data that you'll need. You could have looked it up and do some intermediate calculations, but just to save you the time, you can use the population of 44,000. There's a certain waste generation rate you're supposed to assume, an uncompacted density before they start compressing the waste. And then what you should assume when you're doing problem 11.27 is assume normal compaction. And that'll make more sense to you today after what we go through in our in-class exercise. But there are different density goals that you can achieve when you're packing the waste into a landfill. And so for this problem, just assume normal. All right, so remember when we talked very briefly about landfilling previously in the semester, we were talking about it in terms of trying to preserve the quality of groundwater. That one potential source of contamination is that if we just bury our garbage and our rubbish and our, what are some of the other words? Garbage, rubbish, trash. We bury all those things and the metals and the organic chemicals and the bacteria, all those things filter down into the groundwater, then it can cause problems related to human health. This cutaway shows how sophisticated sanitary landfills actually are. You can see from this diagram that they have wells. Now, these aren't drinking water wells. Nobody would put drinking water wells right next to a landfill because the risk that the water is contaminated, there's even still risk even though we have so many precautionary measures. And so one of the first factors of safety is that you put your drinking water well far away from the landfill. So these wells are actually what are known as monitoring wells. And what they'll do is they'll extract samples, sometimes daily, sometimes weekly, yearly, depending on how old the landfill is and its status. They'll extract samples and they'll test the groundwater for contamination. And if they find anything, if they find any organic constituents or any heavy metals, that tells them that the landfill has failed and that it needs to go in and be repaired. And talk about a dirty job. Going down through the garbage to repair the liner on a landfill would really be fairly unpleasant. Some of the other features on this is you can see that they've got methane recovery and methane probe, because when organic waste decomposes in the absence of oxygen, it forms methane. So that's something that can happen in wastewater treatment in an anaerobic digester. It's also something that can happen inside a landfill, because we have a sealed environment. Oxygen can't go into the landfill. We'll have plastic underneath, plastic on top, and they'll weld the seal. They'll actually fuse the plastic together to make sure that no moisture gets out. And so as a consequence of that, since no moisture can go in or out from the landfill, no oxygen can go in or out. So it doesn't take long for the naturally occurring bacteria inside of a landfill to break down all of the organics and start to form methane. And so sometimes what they will do is they'll capture the methane, and it can be recovered and turned into heat for, if there's an office building related to the management of the landfill, they can heat the office building. Sometimes when they're really ambitious, they'll try and generate a little bit of electricity. Yeah, it can. It can. So I guess there's a geotechnical aspect to this as well. That, remember, we're compacting things to really big densities. The waste itself is being compacted to densities that are sometimes greater than the density of the soil that's surrounding it. And so it can be heavier than the surrounding soil, and potentially the landfill could sink. Excuse me? Can you build over it? Sometimes they'll put things like a ski resort on top of a sealed landfill, but I'm not aware of any place where they put structures on top of a landfill. All right. One other thing I want to point out is that it appears that there are segments in here. These are referred to as cells. You can see that there's individual sort of isolated layers of garbage, and in between the layers of the solid waste there's something called the daily cover. They'll be dumping the waste all day long into the landfill, and then before they leave for the day they'll spread a layer of soil, usually around 15 centimeters. They'll spread a layer of soil on top of the incoming solid waste that's been there that day, just to avoid any birds or wildlife getting into it, and try and keep the odors down, prevent papers from flying away. And so a lot of the volume inside of the landfill is actually allocated to soil. Unfortunately, some of the space that gets taken up is the waste that we're disposing of, and then some of it is this daily cover, and then sometimes there will be additional layers of cover in between intermediate cells, depending on how tall you anticipate the landfill becoming. We'll get into that with our calculations today in the in-class exercise, trying to compare the volume of the waste to the volume of the soil that comes into a landfill. Down at the bottom of the landfill, you can see that they have a series of pipes that are meant to collect any water that might be trickling through. You think about there is water bottles, and we should empty our water bottles before we put them into recycling, because that makes it easier to recycle. Sometimes bottles get into the landfill though, and if there's moisture in them, when the compactors drive over it, it can open up the bottle, and so water is present inside the landfill, and it will eventually trickle downward. And so there's a series of slotted pipes that are down there to collect whatever moisture accumulates at the bottom of the landfill. And so you want to collect that so it can be treated and not pooling on top of the clay layer and the plastic layer at the bottom. So that's another element of trying to prevent the groundwater from becoming contaminated, is collecting leachate at the bottom. And leachate, it's not just water, it's water that's percolated through waste. And so it picks up the constituents of the waste. It's water that's been in contact with batteries, because a lot of people are in the habit of putting batteries into a landfill. And so batteries can have heavy metals like mercury or cadmium, lead. And so the water that's filtering through there is picking up chemicals that it's coming into contact with, and that's why it's so important to collect that and properly dispose of it. Good question. What do they do with that dirty leachate water? If it has organic constituents that are volatile, let's say if there was gasoline or things that will evaporate, then what they can do is they can put that leachate water into a pond and just try and let the water and the volatiles escape into the air. But there will be some heavy metals and suspended solids that stay behind. And so one technique that's used for isolating waste is you make concrete with it. And so you'd take that leachate water and you'd make a block of concrete. Well, then all of the contaminants that were in that water are fixed now. They're in the block of concrete and they're not going to go anywhere. And so then you could landfill the concrete, and the whatever constituents are no longer mobile. Other questions? All right, so I'm going to take you on a little bit of a guided tour of a landfill that's under construction, just so that you can visualize it a little bit better and think about what they're doing. It starts with a site and trying to find some place that's not in anyone's backyard. Because remember that acronym NIMB, not in my backyard. People don't like the odors that are associated with the waste. There's a lot of traffic coming in and out of the area. There are earth-moving equipments that are constantly active, and so it's not only a smelly environment, but it's noisy. It can be congested, and so picking the right spot is important. You have to have land that is suitable for what's going to be done to it. Here you can see that they are rolling out something that's called a geotextile. Sometimes it's called a geosynthetic. It's basically a fabric that you're going to put down underneath a layer of plastic to try and help protect the plastic. And so they will first lay out this fabric onto compacted clay. That's the best thing to have underneath the plastic layer, is usually around 1 meter of compacted clay, selected because it has a really low hydraulic conductivity. Out here in the UAE, I don't think they're using compacted clay because I'm not aware of a good local source of clay. And so, sometimes you have to make compromises. What they could possibly do instead is have 2 separate layers of the plastic, a really thick plastic. It's not just ordinary garbage bags, as you might imagine. It's a pretty heavy-duty, thick layer of polymer that they use. So it can get punctured, and so that's why they're so careful about avoiding construction and demolition waste into a municipal landfill, is because if there's a piece of rebar that goes through the layer of soil that's on top of this plastic layer, it can puncture it, and then all of your efforts are for nothing.
Why don't they test like concrete or something?
I guess probably because it's not necessary and it would be really expensive. As long as they're careful, then they don't need the extra protection that concrete would give them. So as long as they're avoiding like these big pieces of metal that could puncture it, and you'll see in a photo in just a minute, they put down a layer of dirt on top of any place they're going to drive with the equipment, because there's trucks coming to unload, and so they're always careful to have a layer of something so that you're not operating directly onto the plastic. As long as they manage it right, then the expense of the concrete isn't necessary. This is just to give you an idea. The keys that are on this are for scale, to give you an idea that this is a really thick, heavy fabric. This isn't like clothing fabric, but down in the lab they have these bags that you put like concrete in. Have you seen ever before like the heavy-duty bags that crushed concrete can go into, and then a forklift can actually lift the bag and haul it away? It's like the thickest, toughest fabric you can imagine, because a lot of earth-moving equipment is going to be bearing down on that fabric, so it's important for it not to tear. as they lay out the plastic on big rolls, occasionally there can be imperfections in the plastic. It might be that there was a rock that somehow slipped through. There shouldn't be any rocks in the clay that's underneath the geotextile, but inspectors are always on the lookout for sections that need to be cut out and replaced. So they put a patch on a section like that. You can see the consequences of carelessness. The geotextile can rip, and so that whole section would have to be replaced. So they lay out the rolls, and because they're going to need so much more plastic than one roll, you can't have a section of plastic that's 100 meters wide, and so they do it in sections, and then they seal those sections together with thermoplastic welders. And so that's what this process is showing is they have heat guns that can fuse the plastic layers together, and they actually put two different seals to join it. They have an overlapping section of plastic, and then they have one seal on the left, one seal on the right, and let me show you. Okay, yeah, they're heat sealing it here. More heat sealing. All right, this. What they're doing is they're testing to make sure that the heat seal is airtight and watertight. What they're doing is they're pumping up compressed air into the channel between the two heat seals. And so remember, you can get a sense of it in this drawing, that if they do one seal on the right, one on the left, it creates a channel that they can cap at the top and the bottom, and then this should be an airtight section. So they'll poke into it with a needle, use a pump to make sure it can hold a certain pressure, wait for a few minutes, make sure that the pressure is holding. That tells them that the welds in the plastic are good. And so then they pull out the needle, put a patch on top of where the needle hole was, and then that section is essentially one continuous piece of plastic. So it's kind of an ingenious way to make sure that there aren't any holes in the joining of those two sections. No, this is at the beginning of the landfill before the first garbage is brought in. So that's a good question. They would do, let's see if we can get an overview, the final overview. Well, I don't have one of the entire landfill, but they would put in all of the plastic for the whole landfill at the beginning, and then they would load it with the first initial layer of soil, and then they would start to bring in the garbage. And so this is a pretty specialized thing. The people who are laying this out and sealing it together, they travel around the country or the world. They're not staying in the same place every day doing this. Yeah. All right, so I jumped through some of the pictures kind of quickly there looking for an overhead. They pump it up, put another layer of soil on top of it. All right, so when I was talking about being careful, I'm not driving directly on the geomembrane. That's a fancy word for the plastic they've laid out. They call it a geomembrane because it's in contact with the soil. It's okay to even have tracked vehicles going on top of it if you put a reasonably thick layer of soil on top of the geotextile that's on top of the geomembrane. All right. There's a couple of different techniques that are used for the landfilling itself. So let's say we've finished construction. We have this environment with leachate collection underneath. So there's sort of like a series of pipes underneath to collect any water that might get loose. There's the plastic, and on top of the plastic there's soil, so we can drive on it. So what this first illustration is showing that you build cells, and each day you'd put a certain amount of waste, and then in the evening before leaving you'd cover it with soil, and that becomes your daily lift. They sometimes call it a lift when they're compacting a certain amount of waste. And some landfills would maybe have 2 lifts. Some may have many more than that depending on the height that they anticipate to go at. But by contrast to this approach is, you can see in this diagram what they've done is they excavated all of the land out of this, and so they're going below the ground level, and they kind of build up on the sides of the trench where they put the waste. And so here, the main difference, if you look at where the truck that's unloading, the truck is unloading in the second case at ground level, and the waste is actually buried beneath the ground when you're trying not to get too tall. Or sometimes the waste is going to be much taller than the original ground level. So here the original ground level is beneath, and you're just continuing to build taller and taller. When you drive into Dubai, on either side of the road, it's a landfill on 311 from the Dubai-Sharjah border, and they're getting very tall. I mean, that's quite high.
You mean the area of the bridge?
Yeah, yeah, right. So I think it's, as we go from Dubai into Sharjah, just as you hit the border of Sharjah, it's on the right side. Yeah. Here is a table that you'll need to use in the homework and in today's in-class exercise that tells us how compactable certain types of waste are. So you can see that plastic, for example, is very highly compactable because the volume that your water bottle occupies, if you crush it and then put the cap back on, it takes much less volume than it initially does before it's compacted. On the other hand, metals, especially you can see non-ferrous metals, don't compact as well. They can only be made to be 3.3 times as dense. And ashes are even less compactable because even before you start to compact them, ashes are starting to take up as much space as they need. And so we need to create a weighted average of the compactability depending on the breakdown of what percent we have in each category. And that's what we're going to do in the in-class exercise. The other thing I want to point out is just this cross-sectional view of cells, where that's the waste. Underneath the cell of waste is a beginning layer of soil that protects the geomembrane and the geotextile. And then there are layers of soil used as the daily cover. So when we do our in-class exercise in just a few minutes, what you should be thinking about is, as a cross-sectional view, what are the different layers going to look like if you have a certain height that you are limited to? You know, if you're going to lay out the layers of waste in lifts of 0.3 meters, and you have to have 0.15 meters of soil on the bottom and then at the top for each daily cover, then you can calculate how many lifts you can get before you get to the limit of your maximum height. And here's just another cross-sectional view for leachate collection, which these pipes that are underneath would have small cuts in them that allows the water to get into the pipe, and then they drain towards a pump that takes it up to the surface for collection. Does everyone have a copy of today's in-class exercise? All right. So what we're going to do is go through the same process that you'll need to consider in the homework. Let's do these calculations for Sharjah. These are just ballpark calculations. So let's estimate that the population is 1.1 million people. And that's just an estimate because actually the census is going right now. And the latest data I could find was from 2008. So I increased it a little bit from 2008, but it'll be interesting to see what the census actually says the population is. We'll use a waste generation rate of 2.25 kilograms per person per day. And when it's collected, we assume that the waste has an uncompacted density of 150 kilograms per cubic meter. Ultimately, inside the landfill, it's going to be well compacted. So we'll use this column on the right side of table 1110 to calculate our weighted compaction ratio. On the left here, this table is saying how much of the waste is in what category. So 10% of the waste that's collected is food, 55% is paper, and so on. And the reason why you need to know this is to create the weighted average of how compactable the waste is. And so you're going to multiply these mass fractions by the compactability from the well-compacted column. All right. There's a front and back to this paper, and I think what we ought to do is do A through D. So work on A through D. We'll take a look at the solution, and then we'll get started on the back side of the paper, because part E is a little bit weird, and I want to give you some additional guidance once you get to that section. All right, so get started on A through D. All right. So when I was averaging the metals, I mixed up the glass with, it should have been non-ferrous and ferrous, because we're told in the problem statement it's a blend, 50-50 of those two different metal types. So the average, well compacted, should be 5. So I've updated my values to reflect that. So is everybody else getting these same numbers? Yes? Okay. So what do we know so far? What we're saying is, for the waste that comes in every day, we're going to build it up to a height of 0.3 meters. And so we'll put it 0.3 meters, and later on we're going to start looking at how many layers it's going to be and how much soil should be on top of it. But this just tells us the land area that's required each day. Now, sometimes we're going to build on top of an area that has been built on the previous day. So it's not like we need this much fresh land area every day, because sometimes we're going to be putting the garbage from this day on top of another day's lift. But are there any questions so far on these calculations? All right, so the next thing that we're going to look at is, I ask you to draw a sketch in part E. We know that we have a total of 2.4 meters. This is what we're going to do. We don't want it to be taller than 2.4 meters. On the bottom is going to be 0.15 meters of soil. So here's soil, and it's 0.15 meters. In total, it should only go this high. So we're going to have waste, followed by another layer of soil, and so on. So how many days can we stack it up before we get to the limit of 2.4 meters? What I'd like you to do is solve that by just drawing a sketch where each layer of waste is 0.3 and each layer of soil is 0.15. How tall can we get, and how many days worth of incoming waste can be handled by a total height of 2.4 meters? Video here, all right. Okay, so what we have is alternating layers of soil, waste, and soil. The one at the bottom is the protection on top of the liner. And so you can see that here's the first day's discharge, the second day, third day, fourth day, and the fifth day. So if you add up all of those layers together, it should be 2.4 meters. So that tells us the land area that we found in the previous part. It should be the land area of 11,033 square meters. We can use that land area for 5 days until we finished one cell. But we can have more than one cell. We can then start building on top of it again, but what we do is we'd put in a thicker layer. Instead of just having 0.1 meters of soil between cells, it's regulation to usually have more than that. So here in part F, what we're going to say is there should be 3 total cells, where what you're looking at here is only 1 cell. Based on the land area that we found and 3 cells, then how much daily cover is there? We're using the 0.15 meters depth for daily cover. Part G is saying that if we want to have an additional 0.15 meters of soil to separate each of the 3 cells, how much is needed for intermediate cover? And then we cap it with a final cover. So F, G, and H calculate the amount of soil that's required. All right, so here's the idea with the daily cover. The daily cover is, remember, each day we're putting in a layer that's 0.15 meters tall, just so that the birds and the rodents, and so it doesn't blow away. That's what this 0.15 is for. 5 days is how tall each cell is going to get. We're going to put 5 layers inside of our cell, and in the problem statement it said we're going to have 3 of these cells stacked together. So 5 days, 3 cells total, and our land area is what we're going to multiply it by to find the volume. So this is how much soil we need every 5 days to provide that daily cover. You know, it's the last thing they do before they turn out the lights and go home for the night, is they put soil on top of all of the waste just to keep it in place. That's how much you need. Yeah, it's called daily cover because it's put on every day, but the way I've calculated it is how much we're going to use every 5 days, because this area can have more than one lift on top of it. Okay, the next thing we need to take a look at is the intermediate cover. So that's what separates the cells. And so there's a certain volume of soil for that, and the final cover. So those are all expressed on the basis of every 5 days. And so if we want to find it for the total soil per day, then we just divide those 3 volumes added together by 5 days. And so then that gives us the number of cubic meters per day. That's the soil we're using in the landfill. The last steps are to come up with, this is kind of like an efficiency ratio. It's the ratio of how much waste is in the landfill relative to the amount of soil that's in the landfill. And so you calculate E, and well, there's 2 ways to find the total volume. You could just add this number. This is the volume of soil, right? If you add the volume of soil to the volume of waste that we got earlier on, let's see, where did we get that? The volume of waste, here it is, 3309 cubic meters per day. That's the waste. Here's the volume of soil. If you add the 2 together, then that tells you how much landfill volume, including both the waste and the soil, needs to be stored each day. And then if you multiplied that combined volume by the number of days per year and the number of years in the lifetime of the landfill, then that tells you in total the volume that's required for it. Now this other approach, rather than just adding the waste and adding the soil together, the book goes through another idea of calculating the efficiency of the landfill and then multiplying that by the number of people, the waste generation rate. But we kind of already did that. We already factored in the 2.25 per capita generation rate and the number of people. So we could short circuit this intermediate step if we want to. So in the homework, you should go through a similar process of estimating how much volume the waste is going to occupy, how much volume the soil is going to occupy, and then if you know the height of the landfill, then you can calculate the total land area that's needed. All right. So that's all I have for you today. You can set your in-class exercise on the chair on your way out. Remember that this video is posted online if you need to refer back to it again as you're working on your homework. But if you have any questions, feel free to send me a message or stop by my office. I'll see you on Thursday. Wait, no, Tuesday. And Thursday, but before that, Tuesday.